Okay, so in last time we talked about the damped free vibration, and we mainly focus on the viscosity damped free vibration, in which that the damper force is directly proportional with the velocity, and then we reach up to the characteristic equation to find the roots, and the roots can be either real or can be imaginary or double, or imaginary or complex roots. Sharing, I have to make sharing as well. Okay, so we talked about the roots, and according to the radical value, it will be, if it is positive, this is overdamped. If the radical value is negative, it is underdamped. And if it is equal to 0, it is critically damped. For overdamped, there will be no oscillations, and for underdamped, there will be oscillations. And critically damped is the transition between the overdamped and underdamped, and from which we can find the value that makes the system critically damped. This is equality, and then you can find the critical damping coefficient. Then we introduce damping factor, which is zeta. That is the dimensionless parameter C over CC. And also we can write the roots in terms of zeta. Okay, so as you can see, the roots are, if zeta is less than 1, this would be underdamped. If zeta equal to 0, this is critically damped. If zeta equal greater than 1, if zeta is equal to 1, this would be 0, and this would be critically damped. If zeta greater than 1, this will be real value, and it will be overdamped. Also, differential equation can be written in terms of zeta and omega n. Okay, and here I gave an example that we have 2x double dot plus 50x dot plus 500x equal to 0. So we can divide by 2 first. We make the coefficient of x double dot equal to 1. And then the coefficient of x is omega n squared. And the coefficient of x dot is 2 zeta omega n. And from here we can find zeta is 25 divided by 2 omega n, which is square root of 250. Okay, and then we can determine if this value, I think, is let me check the value. So it is 25 divided by 2 divided by 250 is 179, which is less than 1, and this is underdamped system. Okay, so this is the last slide in the lecture about the complex domain of the roots. So the roots will be, this is the complex domain which shows the real axis and the imaginary axis of the root. This is S1 over omega n, and this is S2 over omega n. If zeta equal to 0, okay, this graph is plotted versus zeta. If zeta equal to 0, we will have 2 roots, S1 and S2, are both on the imaginary axis. Roots S1 and S2 over omega n. يعني الريشيو واخدين S1 over omega n and S2 over omega n, and the relationship with zeta. So if zeta is 0, we have 2 imaginary roots. And if zeta is greater than 0 but less than 1, we have complex roots, which is imaginary and real parts. And then if zeta equal to 1 here, we have double roots, which is the critical damping system. And if zeta is greater than 1, root number 1 will go towards 0 if zeta goes to infinity. And second root will go to minus infinity. when zeta is infinity. Okay. If zeta increase beyond unity, the two roots get separated along the horizontal axis and became real. They are, for zeta greater than 1, the two roots are real. S1 will go toward 0, S2 will go toward minus infinity. Now I will talk about the oscillations. You know, this is the free vibration. If you give initial disturbance to the system, let's say you give initial displacement only, it means the mass, if this is a spring mass system, the mass will go back to equilibrium. And it will go back to equilibrium. It depends on the value of zeta. If zeta is less than 1, this will take time with oscillations to reach to equilibrium. And if zeta is overdamped, it will reach to equilibrium with a greater time. And it will take more time than, it depends on the value of zeta, because it becomes very stiff as zeta is very much greater than 1, and it will be very slow system to go back to equilibrium. And zeta equal to 1 will make the system to go, will make the mass to go to equilibrium quickly. You know, this is the fastest, you know, case.
So, overdamped في oscillation?
ما في oscillation. بس الأندر. Okay, it depends on the value of the initial conditions also, but mainly there will be no oscillations for overdamp. Okay, so let's move to lecture 12, which is the continuation. This is page 36. Now we will see the behavior of motion for each case. We have 3 cases: the underdamped, overdamped, and the critically damped. For underdamped, with zeta less than 1, we call it oscillatory motion. The roots become complex, and then you can take I, which is square root of -1, as a common factor, I equal to square root of -1. And then you can switch the terms inside the parentheses. Okay, this will be, it was zeta square -1 in the root. This becomes 1 minus zeta square because zeta is less than 1. And you can use Euler equation for, you know, e to power plus minus I square root of 1 minus zeta squared omega n t. You can use Euler equation, which is cosine square root of 1 minus zeta squared omega n t plus minus. If it means if the power is positive, then we have a plus sign here, addition. If it is negative, we have subtraction. I multiply by sine square root of 1 minus zeta squared omega n t, and those are, this is the argument of cosine and sine, which shows they are the same. Okay, by doing this, we can reduce the equation because I is just a constant. I is a -1. Multiply by A or multiply by B gives you another constant. Yani I times B or I times C times A is just another constant. So we can just write that x equal to e to power minus zeta as it is. You know, this is the same. Okay, and between the parentheses, we will get C1 after using Euler equation, C1, which is a new constant, not A, not B, because A and B multiply by I and becomes a new constant. C1 sine square root of 1 minus zeta square omega n t plus C2 times cosine square root of 1 minus zeta squared omega n t. This is one form of writing the expression or the solution, and you can use the trigonometry identities to get this equation, which is, this one is also valid. And we did this for undamped system as well, that we can either write sine plus cosine or just one term sine with phase. So here is but the good thing about this form, the first one here, is that this is the amplitude and this is phase. So you can amplitude, but this is changing, and this is phase. Okay. So whether we can use one of them, any one of them, that X and phi or C1 and C2 are constants that comes from integrating and solution of the differential equation, which are determined from the initial conditions. The initial conditions, as usual, for second order ordinary differential equations are X at 0 and X dot at 0. The second form, which is this one, C1 and C2 are found. Okay, it's just mathematical steps here we need. So C1 becomes X dot at 0 plus zeta omega n X at 0 divided by omega n square root of 1 minus zeta squared. This is C1. And C2 is only X at 0, the initial displacement. Now this is the equation for the response. And as you can see from the argument of sine and cosine, this should be in radian. Then T, we know it is in seconds, right? T is in seconds. Therefore, there is a frequency of oscillation here is square root of 1 minus zeta squared omega n is the frequency of oscillation. Okay, the argument should be radian, and there is time is second, then the rest should be radian per second. And this is called the frequency of oscillation. And the frequency of oscillation here is for the damped system, and it's also called natural frequency. So we have omega d equal to, the argument without t, which is 1 square root of 1 minus zeta squared omega n. Or, it is omega n square root of 1 minus zeta, square root of 1 minus zeta squared. And this is called natural frequency of damped oscillation. So there is two definitions for natural frequency. Natural frequency of damped system. And omega n is also a natural frequency, but for undamped system. So now we have to be specific that the natural frequency is the frequency of oscillation of the system under the free vibration. If the system is undamped, it's going to have omega n. And if the system is underdamped, the frequency of oscillation will be omega d. Okay, and that is to be clear, because if the frequency of oscillation is given a value, then we have to know this is omega n or omega d. So if the question says that the frequency of oscillation is 2 radian per second, I cannot say this is omega n or omega d unless I know the type of the system. So the first thing I have to know is to calculate zeta. Zeta 0, this is omega n. Zeta is less than 1, this is omega d. And the omega d equation is not square root of k over m. It is equal to omega n square root of 1 minus zeta squared. Omega n is as before. There is no changes in omega n, square root of k over m. Okay. And zeta here is less than 1. What is tau d? Tau d is the period of oscillation of the damped system. There is tau n, which is the period of oscillation of undamped system, and here we can see there is tau d, which is the period of oscillation of the damped system. Again, if the time is given, it says period of oscillation is 1.2 seconds. I have to know what is the value of zeta to say whether this is undamped or overdamped or underdamped. Okay, so the frequency of oscillation, if the system has a viscous damper, is altered from omega n. It's not same as omega n. Yani the spring mass system under free vibration will have a frequency of oscillation equal to omega n. If you add a viscous damper so that it is underdamped, omega is not omega n. The frequency of oscillation is omega d. But omega d equal to omega n square root of 1 minus zeta squared. And I think I put this one in the formula sheet as well. Zeta is the damping factor. Zeta is C over Cc. Okay, Cc is a parameter of a system, of the system. It is not the given value of the damper. The given value of the damper is C. And Cc is like omega n, square root of K over M, characteristic of a system. Cc is also characteristic of a system, which is determined from K and M. That is Cc. So Cc is equal to 2 square root of Km. So it is not related to C. So even if it is undamped system, both have the same Cc. The Cc here and Cc here are the same. The critically damped coefficient for both systems are the same. But C here is 0. So zeta is equal to 0. C here is some value less than Cc and make zeta less than. Okay.
So إذا قدرنا نعوض الإكس بالدبليو ومو
نعوض في الإكس يعني this equation. Yeah, there is omega. This is called omega d now. The whole thing here is omega d.
يعني في الإكس دوت أو 0 بلس زيتا دبليو إن ولا
لا omega. Okay. I'm only saying that the frequency of oscillation is altered to omega d rather than omega n. So if you add a viscous damper so that the system is underdamped, the frequency of oscillation will change to omega d instead of omega n. But this is, you use this as omega n. There is no trick here. This is omega n is as it is. Only this is omega d. So you can simplify this if you want, equal to e to power minus zeta omega nt times C1 sine omega dt plus C2 cosine omega dt, just to make it shorter. Now, typical response of underdamped is, as we said, it is oscillatory. Here, a typical response given for for initial condition x at 0 greater than 0 and x that at 0 is greater than 0 as well. Both are positive. Yeah, initial displacement is positive, initial velocity is positive. So at t equal to 0, this is equal to x at 0, which is equal to x sine phi. He's using this expression. Okay, when you put t equal to 0, this will be sine of phi, and e to power 0 is 1, and this will be x sine phi, x sine phi. This is x0. But it is not, because of the initial velocity is greater than 0, it will overshoot. It will go farther downward. So the system is given initial displacement, which means you push it downward, and you give initial velocity as well in the same direction, so it will go farther downward. And this is called overshoot. That will reach, the overshoot is the maximum peak. The maximum of all. This is the overshoot, which is the maximum amplitude. Okay, and you can find, the time to find the overshoot. Or maximum amplitude. You will put dx by dt equal to 0, which is the velocity. Okay, this is the velocity should be 0 at maximum. Okay, if you give initial conditions, here both are positive and all of them are not 0. So suppose x at 0 is greater than 0 and x that at 0 is 0. Then the response will be directly, it will come from x at 0 and then drop without overshooting. Okay, this will go downward without overshooting. No overshoot here. It will overshoot on the other side, the negative side, but there is no overshoot in the positive direction. Okay, if you give initial velocity but no initial displacement, so it will overshoot and then decay. So x at 0 is 0 and x that at 0 is greater than 0. There will be overshoot here. And if you give negative initial velocity, it will overshoot in the other direction, in the negative direction. Okay, in any case, this negative frequency of damped oscillation is the same. There is no changes because it does not depend on the initial conditions. Okay, so the characteristics of underdamped, it is oscillatory motion all the time. Okay, if you have zeta greater than 1, this is the overdamped case, and for overdamped there is no oscillations. The roots are real, and we have exponential functions, okay, which is a e to power minus zeta plus square root of zeta square minus 1, omega nt plus b e to power minus zeta minus square root of zeta square minus 1 omega nt, and a and b to be found from initial conditions, which are given by those expressions for a and b. A is x that at 0 plus zeta plus square root of zeta square minus 1, omega n x at 0 divided by 2 omega n square root of zeta square minus 1. And b is minus x that at 0 minus zeta minus square root of zeta square minus 1 multiplied by omega n x at 0 divided by 2 omega n zeta square minus 1 in the square root. Okay, the function is exponentially decreasing as expected because this is the function and referred to as a periodic. There is no oscillations here. And if there are no oscillation, there is no frequency of oscillation. Yeah, it is not sinusoidal. There is no sine functions here. So there are no oscillations, and then there is no frequency of oscillation. So if it is overdone, it will oscillate. It will not oscillate, and that omega d you can assume it is 0. That there is no frequency. Omega d, but not omega n.
إذا عوضت معادلة مال أوميجا دي بيطلع لنا جواب فيه imaginary.
We don't substitute in omega d. So just take omega d is 0. Take omega d 0. Okay, this is a typical response again with x at 0 is greater than 0, x that at 0 is also greater than 0, and there is overshoot. Okay, overshoot, and at overshoot, you know that dx by dt equal to 0. So if the question is to find the maximum amplitude, you need first of all to take dx by dt equal to 0 to find the corresponding time, right? And then substitute in x with that time. Okay, other responses might be, for example, initial displacement is 0 and initial velocity greater than 0. So this will overshoot and then come downward. No oscillations, but there is a peak here and overshooting. For critically damped, we have double roots. If you go back to the same equation, it means and substitute, you will get only one solution with double roots. So the second solution is the usual procedure is for a second solution is to multiply the first solution by t. It's like polynomial order. The second solution is required. You multiply the first solution by t. As you can see, a times e to the power minus omega n t. Zeta is not shown here because zeta equal to 1. So it is e minus omega n t times a. This is the first solution. The second solution is multiply the first solution by t with another constant plus b times t e to the power minus omega n t. A and B again are found from initial conditions, which is reduces to x equal to x at 0 plus x that at 0 plus omega n times x at 0 times t, which is this is b in the bracket, times e to the power minus omega n t. And here shows the typical responses for different initial velocity. We have x at 0 is positive, and initial velocity is one response for positive equal to 0 and less than 0. Okay, so with x dot at 0, which is the initial velocity, if it is greater than 0, there will be overshooting here. Again, at overshoot, we have dx by dt equal to 0. Okay, this is at overshoot, at maximum. Okay, if x dot at 0 is 0, this will decay exponentially without overshooting. And if x dot is negative, then it will overshoot in the other direction, in the negative side. Okay. I added this example. So there are, in summary, there are three cases, three dam systems. The equation of the response depends on the zeta. So we cannot find the response before finding zeta. You cannot find the frequency of oscillation before finding zeta. So that's the two steps you have to do. Okay, you find zeta, you find omega, and you find zeta. If zeta is less than 1, this is oscillatory, and there is a frequency of oscillation is not 0. Omega d. If zeta equal to 1, then omega d is 0. Zeta greater than 1, omega d is 0. No frequency of oscillation. The system is not oscillating. Here is an 8 kilogram body is moved 0.2 meter to the right of the equilibrium position and released from rest at t equal to 0. So we have initial displacement equal to 0.2 and initial velocity is 0. The spring stiffness K is 32 Newton per meter. Determine the displacement of the body at t equal to 2 seconds for c equal to 20 Newton second per meter. So the first step is to find omega n. This is spring mass system. I don't have to work on the equation of motion to find omega n. If it is a rigid body, it means I have to find, first of all, the equation of motion, then find expression for omega n. But this is a spring mass system with damper. I know what is omega n as we did in the previous lectures. So I use the result of what we did. So omega n of such system is square root of k over n. Okay, if there is springs in series or in parallel different arrangement, you have to find K equivalent. Okay, so omega n is square root of K over M, 32 over 8, under square root, it is 2 radian per second. Zeta is C over 2M omega n, which is C over CC. And one of the equation for CC is 2M omega n. And substituting, we get zeta is 0.625, which is underdamped, less than. Okay, since zeta is less than 1, the system is underdamped. The damped natural frequency is omega d, equal to omega n square root of 1 minus zeta squared, equal to 2 times square root of 1 minus 0.625 squared, equal to 1.561 radian per second. This is relatively high, zeta, 0.6. Okay, in practical systems, which rely on structural damping, they will have zeta very small, 0.1 maybe maximum, and that omega n and omega d are almost the same for small zeta, but here this is relatively high. And as you can see, omega n is 2 and omega d is 1.561 radian per second. And you can find the response. The question is to find the displacement at t equal to 2 seconds. Since this is underdamped, I will use the equation of underdamped. So it is given as x equal to c, which is, we called it before as capital X, which is a constant. Okay, so we use before capital X because I use this from different reference. So x or c e to power minus zeta omega n t sine omega dt plus psi or phi, which is phase. Those just our names. And c, okay, he's putting the values for omega n and zeta and omega d. So it is c times e to power minus 1.25 t sine 1.561 t plus psi. The velocity is okay, so he's doing substitution of the initial conditions. The velocity is required because it's 0. We need two equations, minus 1.25 c e to the power minus 1.25 t sine 1.561 t plus psi plus, you take the derivative of sine of the exponential function multiplied by sine plus the exponential multiplied by the derivative of sine, which is cosine. Plus 1.561 c e minus 1.25 t cosine 1.561 t plus psi. Now evaluating the constants at from the initial conditions, we have at t equal to 0, x at 0 is equal to 0.2, and when you substitute, you get it is c sine phi. This is one equation. The second equation is the velocity equal to 0. And the equation of the velocity is minus 1.25 c sine phi plus 1.561 c cosine phi. So cosine c sine phi, you can substitute it here, and then you can get equation for cosine phi, or you can get equation for c cosine phi. Okay, with this, okay, you can put c sine psi equal to 0.2, and also you can get c cosine psi equal to 1.25 multiplied by c sine psi is 0.2 divided by 1.561. To get c, you can square both equations, okay, and then add them together. Then sine square psi plus cosine square psi is 1. And then you can get c from here. Okay, so this is equation 1, equation 2. So 1 squared plus 2 squared will lead to find c. And then you can substitute in one of the equations to get psi. Okay, so the answers are C is 0.256 and psi equal to 0.896 radian. This is in radian. And even if you get this in the calculator, use use the radian mode, not degrees. Okay, and this is the final equation for the response. X equal to 0.256 E minus 1.25 T sine 1.561 T plus 0.896. Evaluation for T at time T equal to 2 seconds, we can substitute for X at T equal to 2 is minus 0.01616, and try this yourself to get experience. Okay, because you need to substitute. This should be all in radian, and your calculator has to be on the radian mode, or you use Excel. Excel by default is radian. This angle should be in radian. The typical response, of course, for this equation will be starting from 0.2, and it will oscillate. Okay, if you want to find the maximum, okay, you need to differentiate this with respect to time. Okay, which is already obtained here. So you can substitute for the value of C and the value of psi, and then find the time at which that velocity is 0 or X is maximum. Okay, so you can evaluate maximum. Okay, which is the overshoot. Okay, so we can get this X maximum occurs when the velocity is 0. So you take this minus 1.25 C e to power minus 1.25 T sine 1.561 T plus psi plus 1.561 C e to power minus 1.25 T cosine 1.561 T plus psi equal to 0. So as you can see, C and exponential terms will cancel out. And then you can divide by cosine and get tan. So tan 1.561 T plus psi will equal to 1.561 divided by 1.25. Okay, and once we know this value, psi is 0.896, and from here you can find the time. Okay, and that will give you the corresponding time, and then you substitute in X to get the maximum. Okay, so this T, let's call it Tm, then X maximum is equal to X at Tm. Okay, any questions so far?
X maximum.
Yeah, it's the amplitude, yes. Amplitude, but at the maximum value. We have a few minutes. Logarithmic decrement is a convenient way to determine the amount of damping present in a system is to measure the rate of decay of a free vibration. And this is related to underdamped system. Okay, the larger the damping, the greater will be the rate of decay, and this is for underdamped. This decaying of the vibration depends on the value of zeta. The number of oscillations depends on the value of zeta. Okay, let's see how we can get this decay and the relation of zeta. As you know, for underdamped, X can be written as X e to the power minus zeta omega n T sine square root of 1 minus zeta square omega n t plus psi. There is a logarithmic decrement defined as the natural logarithm of the ratio of any two successive amplitude. The successive amplitude, if you take x1 at times t, t1, and x2 at time t2, t2 is equal to t1 plus tau d. This is called successive amplitude. That the separation or those two amplitudes are tau d apart. The time between them is one oscillation. That's called successive amplitude. Okay, so you can take any two successive amplitude, positive, positive, or negative, or negative. So this is the definition of the logarithmic decrement, that delta equal to ln x1 over x2. x1, it means at time t1, which when you substitute, it is e minus zeta omega in t1 sine square root of 1 minus zeta square omega in t1 plus phi. Okay, here is t1, here is t1. Divided by e to the power minus zeta omega in t2 is t1 plus tau d sine square root of 1 minus zeta square omega in t1 plus tau d plus phi. Now this the two sine terms will be the same at time t1 or at time t2 because they are separated by tau d because sine is periodic. So sine at T1 is same as sine at T2, the same amplitude. So you can cancel those two. They cancel each other. The remaining will be only the exponential terms. So e to the power minus zeta omega in t divided by e to the power minus zeta omega in t1 plus tau d, we can take this to the numerator. We can take this up. And it means they have the same base, which is e and e, but the different exponent. Okay, so delta becomes simplified ln e to the power minus zeta omega in t1 divided by e minus zeta omega in t1 plus tau d equal to ln, you can take this up, and this will be ln of e to the power zeta omega in tau d, because this will cancel with this as well. So you have e to the power zeta omega in tau d, and you can use the properties of logarithms. You multiply the power in the front of ln. Then ln of e is 1. And this will reduce that delta will equal to 2 omega n tau d. Okay, tau d is 2 pi divided by omega d for underdamped. This is the whole thing is in the denominator. So when substituting for tau d, we get delta equal to 2 pi zeta over square root of 1 minus zeta squared. So this relationship is independent of time. Delta is only dependent on zeta. So if you take another two successive amplitude, yani x2 and x3, you will get the same equation. This is not related to time. As far as the two amplitudes are considered with tau d apart. So this will be the same. So this is the ratio. This is the logarithmic, which is constant for a given system. This is called exact equation. If you want to approximate for zeta less than 1, yani very much less than 1, we know that zeta is less than 1. But if it is very much less than 1, then zeta squared, square root of 1 minus zeta squared become 1. And then the simplified, this is the approximated equation for delta equal to 2 pi zeta. Delta, now how we can find zeta experimentally? You can conduct an experiment and get the wave of oscillation, recorded. And then you can use the definition of delta, which is delta equal to ln x1 over x2. You can measure x1 and you can measure x2 on the graph. Okay, so we measure x1 and we measure x2 from the recorded graph. Then delta is equal to ln x1 over x2. We substitute this here and find zeta. Okay, if this is experimentally, you can find zeta from this equation by first of all calculating delta from the recorded graph. Okay, and we can do this next time, example 12. Yeah.
الابروكسيميشن لما قلنا سكوير روت مال 1 ماينس زيتا سكوير يعني لما تكون فيري سمول يعني تقريبا زيرو فيتربيوت تو 1 صح؟
صح.
زين ليش دكتور في المعادله مال دلتا لما قلنا دلتا تساوي 2 باي زيتا ليش ما قلنا دلتا تساوي زيرو؟
Zeta equal to 0, then delta will be 0 as well. This is zeta squared. So zeta squared, if zeta is small, then you can ignore higher order of zeta. And zeta small, zeta squared become even smaller, so you can neglect the smaller. And become square root of 1 is 1. But zeta, you should keep it. Because that is the order of approximation. It's zeta, not zeta squared. Okay, so we will continue, inshallah, next time. If you have any questions about the marks of the quiz. No? Okay, so everybody is happy with the grade, right? Average is for this section is 7.5. 7.5. And for section 2, 7.23. Okay, see you.